All right, and I hope this is going to be the last video of this series. This is part C, and we are still in chapter 3, section 7, and we are still dealing with optimization. So I'm going to knock out 2 more optimization problems so that you can have some exposure to some different types of questions. But to be honest, the only way that you get better at this is to jump into some practice problems and try them. It should go without saying that that is all of mathematics. You have to do mathematics to get better at mathematics. It is a contact sport, if you will. So let's jump in to this question. So it is going to be another maximization problem, an optimization problem, and it appears that what we have is a rectangle bounded by the x and the y axis. Okay, now, so I've already produced a picture for you, but just to walk you through this. So bounded by the x and the y axis, okay? So that means that the x-axis and the y-axis serve as some walls to box in this rectangle, right? Now, it's also bounded by, so the x and y axis and the graph of 6 minus x over 2. Now 6 minus x over 2 is just a line. And what you can see is that you have this line running as follows. So now you can see that I have, at this stage, we have been able to box in, right, some region of the graph. All right. And now the question is, what length and width should the rectangle have so that its area is a maximum? So does it make sense to you that, take this point right here, as I start to move this point up or down, if I move it up here, the length and the width are going to change. If I move this point this way, the length and the width are going to change. And I'm able to, in other words, I can move this point anywhere I want on this line. And I don't care where I stop, but what I, in the sense that, but I do want the rectangle that's formed to be a maximum. So the question now becomes, what xy value would produce the maximum area for this inscribed rectangle? Okay, so step 1 has already been done for us, right? That is draw a picture, try to get a feel for the problem. Step 2 was to see if you can find some equations, some formulas that relate these quantities. Now, I like these problems when they give me an equation like y equals 6 minus x over 2. You can just bet, now this is not always assumed, but you can almost bet that if they give you an equation, this is going to be the secondary equation. All right, so we don't have to go hunting around to try to find a secondary equation. They've actually already given it to us. But we still need the primary equation. And to answer the question of what's the primary equation, well, you should ask yourself, what are you trying to minimize or maximize? So since we want a maximum area of what? Area of a rectangle. Well, the area formula for a rectangle is area is equal to length multiplied by width. Now, the only difference is, instead of me using an L and a W, I'm going to use area is equal to x times y. Okay? And that makes sense because if you look at our secondary equation, that has our secondary equation doesn't have L's and W's, but it has X's and Y's, and we can think about length and width in that fashion. So beautiful. So I'll go ahead and label, but obviously this is going to be the primary because that is what you're trying to optimize. All right, well, hopefully you can start to anticipate my moves here. So step 3 is always a substitution step, right? But just don't get confused. We sub into the primary. Now, this equation is already solved for y. So what you're going to see me do is I'm just going to replace 6 minus x over 2 in the area equation for y. So now it looks like this. Area used to look like x times y, but now its area is equal to x times 6 minus x over 2. Same area equation, but now I only need one variable. All right, so I can make, since I'm going to have to take a derivative of this in just a second, I may as well go ahead and, before I write step 4, I may as well go ahead and multiply this out and distribute everything. So you can imagine I'm going to distribute the x, and we end up with area is equal to, I'm going to write it as 1/2 times 6x minus x squared. In fact, of course it's up to you. There is no difference between dividing by 2 and multiplying by half. Same result. But I think you'll find that if you write division problems as multiplication by fractions, life is actually a lot easier for you. So steps 1 through 3 are done, and now comes the calculus step. So now we take the derivative. So listen to some of my advice here, because I've seen very clever students make the same silly mistakes over the 10 years I've been teaching college mathematics. And some of the mistakes are students, well, let's just start with step 4. Students take the derivative of the wrong equation. You remember, you're going to take the derivative of the primary, okay? So step 4 is going to be find, I'll go ahead and write find the a prime. Right? And of course, a prime is the derivative of the area with respect to x. Ready? Let's go ahead and find this. So in this case, the derivative of our area function with respect to x is a fairly easy derivative. That's going to be 1/2. The derivative of 6x is 6. The derivative of minus x squared is minus 2x. Okay. So now we have a derivative. And we are going to set our derivative equal to 0 in this next step. So let's go ahead and turn this into 0 is equal to 1/2 times 6 minus 2x. Okay. So in this case, what we find is that x is equal to 3. So what did you just find out? Well, the picture is quite telling, isn't it? That if you were looking for some xy point and you just figured out that you should choose 3 for x. All right, well, let's actually figure out what the maximum area is. So if you choose 3 for x, we can plug 3 in for this y equation and figure out what y will be. So if I plug 3 in for x, I will get back out, I think it's 1.5, so 3 over 2 for y. Okay, so let's go and answer, what is this maximum area? Well, since area is x times y, this would be 3 multiplied by 3/2. The maximum area that you can get is 4.5. I don't have any units, so whatever units that we're dealing with squared. So 4.5 square units. Okay, so notice that I didn't consider, I basically, as soon as I found that critical number, I went right with plugging it in. I didn't take time to consider the endpoints. So let me make sure you understand why I didn't even waste my time with the endpoints. So what is, let me go ahead and erase all of this. So can you and I agree, let me get a darker color here. Can you and I agree that the minimum value of x to be bounded, it would be 0, right? And the maximum in this case would be 6. But do you even have a rectangle? If you, right, you have no rectangle. You either have all length or all width, but you don't have any two-dimensional rectangle to take an area of. So of course, that makes, I mean, I could show you if you plug 0 in for x, obviously you would get a 0 area, and if you chose the other point, if you plugged 0 in for y, you would get a 0 area. So in this case, clearly, the only x value that we have to consider is the critical value. Let's let this be the last problem. Okay, not that it's easy, but let's let this be the last one. Okay, so you've been along for the ride, so stay awake, stay caffeinated. Let's finish strong. Okay, so ready? So we have a rectangular package you're going to send by a postal service. And now if so say you're going to send it priority mail or some other type of mail, whether you're dealing with FedEx or the post office, they have restrictions, right? They have certain constraints. So so I don't know what they are off the top of my head, but you might be something like you can't send a package priority mail if the box is too large, right? Let's just say it like that. So now let me continue to read. So you're going to send some type of rectangular package, and you're told that it can have a maximum combined length and girth. Now, what does girth mean? Well, the girth is just the perimeter of a cross section, and I'll make sure you know what that means in just a second. But obviously, this box has a maximum, right, amount of size to be sent. So combined length and girth of 108 inches. So that's why a lot of times if you walk into, say, the post office, they will get a tape measure out and they'll start to measure a box just to make sure that it meets the requirements before it can be sent. Now, our job is as follows. We want to find the dimensions of this package, right? So the length times the width times the height that produce a maximum volume. Right? So let's see if we can start to piece some things together. Well, I'm going to use this figure that was provided for this problem. And one of the things that I'm noticing in this figure is that we have these square ends. X, the length of x is the same for both of these dimensions here. And then we also have a y. So let me start with the volume formula for any type of package like this. So the volume is going to be equal to the length times its width times its height. And that's what I want to maximize. So I can do a little bit better than this, though, because in this case, I can have x as a length and x as a width and y as a height. Now, it doesn't matter to me if you call y length or y height or y width. None of that matters, because you can tip the box over and change what you mean by length, width, height. That doesn't matter to me. Mathematically, the multiplication of x times y is equal to y times x, etc. So really the volume formula is equal to x squared times y. Now we're getting somewhere. Okay, it's getting a little bit better. So obviously, since this is going to be the primary, because that is the thing that I want to take, that's the thing I want to maximize. So now comes the part where we have to reach into our geometry bag and try to figure out this perimeter of a cross section, right? So the maximum combined length and girth. So how do we go through the maximum combined length and girth? Well, you would think about if you were going to run a tape measure, you would measure obviously y. So it's going to be y plus what? Then you would measure the distance here, the distance here, the distance here, and here. Right? So you would, in other words, you would measure all the way around the box. So let's put that together. Let's put that into something, right? So what we have in this, the combined length, I'll just write this, combined length and girth. Ready? Let's go ahead and start to add that up. So if you had your tape measure and you started adding that up, so it would be y plus x plus x plus x plus x, so y plus 4x. With me? All right, and now we know a little bit more about this. We actually know the constraint, right? Remember, it says that it has to be a maximum of 108 inches. So when you add up all those lengths, the maximum it can be is 108 inches. So that leads me to the following. I have 108 is going to be equal to y plus 4x. All right, so those are the first two steps, and don't let those first two steps confuse you, because we are somewhat spoiled because we already have a picture, and you are somewhat spoiled because you have someone who already has the answer, right? So those first two steps, in my opinion, are the hardest steps. I have said many times I wish we could take K through 12 and spend all of our time, instead of rushing through to get to calculus, spend all of our time modeling. Just modeling real world phenomena, taking word problems, turning them into pictures, etc. I think that we would have a different caliber of math student. All right, so it's at this stage where, that's steps 1 and 2. So it's at this stage, right, at step 3, where you have to start to substitute. So if you don't mind, let me pose a question to you, and you can pause it if you'd like to consider it. But what are we subbing? What are we going to solve? Which equation are we going to solve, and which equation are we going to sub into? Well, hopefully you've considered the question, but you always substitute into the primary. Right? The secondary equation is just a way of rewriting the primary equation. So, all right, ready? I'm gonna solve the secondary equation. So this is the last problem. So let's finish strong. So I have 108 was equal to y plus 4x. Let's solve that for y. So that means y is equal to 108 minus 4x. Beautiful. So now, wherever I see y, I can rewrite that in terms of x. So I'm going to substitute into my volume. So ready? Here we go. So volume was equal to x squared multiplied by y. But now this is going to be plugged in for y. So now let's finish it. So now I have v is equal to x squared multiplied by 108 minus 4x. Okay, so step 3 is done. Now is when you are going to start to do some calculus. I think you will find, not that this matters, but I think you'll find life a little bit easier if you go ahead and distribute this x squared. So now we have 108 x squared, and then what would that be? Minus 4x cubed. Okay, ready? So let's go to that 4th step. Now we take the derivative, and so find v prime. All right, ready? So v prime is equal to 216x minus 12x squared. Okay. Step 5 is going to be to find that critical number. So we're going to set v prime equal to 0. So now I have 0 is equal to 216x minus 12x squared. All right, ready? Let's solve for x. So pretty easy. We can factor out, let's see, factor out a 12 too. So 12x, and that would leave us with 18 minus x. That tells me that x can be 0 or 18. All right, so I'm going to go to the next page here, and so I can give myself some more space, and then we're going to try to figure out which of these values is going, or how do we figure out what the max is and what the dimensions are. Ready? Let me go to the final page. So we left off with x was equal to 0 and 18. And remember, we're looking for the dimensions, a length times a width times a height, right, that produce the maximum volume. Okay. So in this case, I'm going to have to go back to the previous pages and grab, well, actually, let me see if I can, yeah, let me go back to the previous page and grab any type of formulas that I need. So I'm going to go ahead and grab that volume formula for right now. So V was equal to x squared times y, but we were able to rewrite V as let's see here, 108, I think it was 108 x squared minus 4x cubed. Let me double check that. Perfect, okay? Okay, so let's see what happens. So if we plug, I think we can agree that if you choose 0 for x, you're not gonna have any volume because you don't even have a box. You just have a flat piece of cardboard. If you were to plug in, choose 18 for x, well, let's see here. I don't have a calculator readily available. But that should be 11,664 cubic inches. Okay. I did not do that in my head. I have it written down. Unfortunately, my eyesight is not the greatest, so I hope that 108 times 18 squared minus 4 times 18 cubed indeed produces this this volume of 11,664 cubic inches. So that is going to be your maximum volume, but do you agree with me that that was not the question? The question was, what's the dimensions of the box? A length times a width times a height. Now the only difference is we just said it's x. Now I'm going to remember, we didn't use L's and W's, right? We used X's. So x times y. So I know that the box is going to be an 18 by 18 by, but I don't know that last dimension. So what you would do is, again, as long as you're keeping your work nice and neat, you would just scroll back and find the equation that gives you a y if you give it an x, right? So y is equal to 108 minus 4x. So if y is equal to 108 minus 4x, what am I doing right now? Well, I know it's an 18 by 18 by something box. I got to figure out what that something is. So if I plug in x equals 18, right, and for x, then what I have is y ends up being 36. So an 18 by 18 by 36 box. If you don't mind, I'm going to grab my cell phone in real time. I'm going to grab a calculator. 18 by 18 by 36, 11,664 cubic inches is the correct volume. If you were able to do that in your head, congratulations. That's a nice trick. It's trivial, but it is a nice trick if you were able be able to do that in your head. For the rest of us, we're going to outsource those types of questions to technology, or by hand. This is your answer. All right, that concludes 3.7. I will see you soon.